Good morning, I'm Cody Henriksen. Today we're going to be talking about Java primitives. We want to do a quick little overview of how they are basically set up and a little introduction of what's going on with them. So let's go ahead and take a look at this. When we're talking about Java primitives, we're talking about the really built-in the building blocks of what make up Java. They're the really tiny pieces. These are the things that we use when we're trying to talk about very basic data types. Things like numbers, letters, and true and false values are the main ones that we work with this. There's a couple others that are in there. They're numeric really, but those are the ones we really talk about. Counting numbers, decimal values, and Booleans. One of the key things on them is they're very simple. They are not objects. They're just a value itself, nothing special, and they're functionally free. Because they take up so little space, there's very little worry about how much memory is actually involved in the usage of a primitive value because they're tiny, they're free. We first want to look at the numeric types. There's two major numeric types of primitives that we'll use every single time we're working with primitives in a Java program. We have our int type and our double type. The int type are the counting numbers, the integers, the numbers you've been working with since you were a small child. 1, 2, 3, 8,064. Well, I don't have that many fingers, but you get the idea, right? What we have right here is a range of plus or minus 2 billion. Now the negative is a little bit bigger. It has one more because of the way we work with what's called 2's complement storage. But it's plus or minus 2 billion in storage right here. And it's only the whole numbers. None of the infinite range that exists in between those values, just the basic counting numbers we know and love since we're small little rodent children. The next major data type that we're working with when we're talking about primitives are the doubles. The doubles are the infinite value, the set of real, capital R. You know those numbers that exist. There's an infinite number of values between 0 and 1, infinite number of values between 1 and 100. Okay? Same kind of approach. But in this case, we have basically plus or minus 2 times 10 to the 306th-ish. It's functionally redonkulously huge. Okay? 306 zeros. I'm not going to draw this out on the board. That's just crazy. But that's how many zeros we're talking about. It also includes, wait for it, positive infinity, negative infinity, and nan. What nan? Nan's not a number. Exactly. Nan, the not a number concept, is how we represent the amazing power of both positive negative and negative infinity at the same time. Say, for example, when you divide by 0. It's a problem when you do it with an int. In double land, totally okay. And we'll talk about that more another time. These, like I said, again, are the set of reals. So if you're talking about your math idea when you're looking at the domain and the range, this is the set of reals. This is the set of whole numbers plus or minus 2 billion. Big, huge amount of space. Not quite as huge, but still, no one's counting to 2 billion. We're good to go. We have our other numeric types. Now, inside primitives, the rest of them are most of the ones we're working with are numeric. So we have the byte, the short, the long, and the float. The byte, short, long, and float are the other major numeric primitive types that exist in Java. Now, as part of the AP Computer Science side, we don't really work with them as part of the official subset or what's covered by the course and exam description. But we do sometimes want to work with them when we're talking about some of the bigger issues of stuff. Say, for example, we want to play with some large numbers to do a quick little demo of recursion. They're a great thing to do. But we have our byte range. We have plus or minus 128 to 127. Oh! So negative 128 to 127. Again, you can see this really well in the 2's complement value because of how much a byte represents. A short is plus or minus 32,000. Oh, yeah, we don't really need to worry about that very often. So short, I never use. I mean, I've literally never needed to use it in any program I've run. If I was really concerned about memory, that's another thing entirely, but not anything I've done with Java. In long land, these are ones we play with when we're talking about using some fun things like factorial and Fibonacci sequence because they get so big so fast, and we want to talk about whole numbers with that. And that's plus or minus 9 quintillion. I mean, plus or minus 2 billion was huge, but 9 quintillion? We're going way beyond the realm of anything we have to ever account. So, yeah, no, we're good. And finally, we have float. A float is half a double. Yeah. Originally, that's all we had were floats, and doubles were double the size. So we use doubles, as a special case. But now we have this huge major amount of space, and it works the same, and double's easy to remember. So that's plus or minus 2 times 10 to the 38th power. And with the float, we have about 7 or 8 digits of precision. On double land, we have 15 digits of precision, so we can specify how much data is on there. We also have char. It's kind of in the other numerics category because a char is really just a short, but holds single Unicode values like A, 7, the question mark, and anything that you can store within a single Unicode value like that. And so it's nice, it's okay. It's an old way of handling text. No emoji though. Here, I know. Everyone's sad. And so this is again why we use strings instead of chars because, well, a string is actually much more efficient and can represent real values of languages beyond simply just English. And so again, char, it's basically just a wrapper around a short. So, yeah, no. The best of all the primitives, though, the most amazing primitive, is the Boolean. Our Boolean type is how we determine true or false. It's what becomes the foundation of computer science logic. And so this is something we use all the time. Boolean expressions, De Morgan's law, using complex evaluation, everything that goes inside an if block or a while loop. We use this every single time we're doing programming. And it all comes down to these two simple, easy peasy values, true and false, lowercase, of course, no caps. But that's what the main primitive we'll be working with on a regular basis, because everything turns down to either true or false when we're talking about a programming logic system. And so Boolean is the main primitive we have to talk about. Especially, it's the only primitive that's not numeric. Because remember, char is just really a wrapper for a short. Because primitives are so itty-bitty things, and Java is trying to be an object-oriented program, we have to have a way of handling those itty-bitty things, those primitives, in the objects that are designed to only work with objects. We have the collections class. We have an array list of type. We can't put little ints inside there. We can't put even huge giant little doubles in there because, again, they're too tiny. They don't fit inside an object box. And so to handle that, we have what are called the wrapper classes. The wrapper classes are what we use so we can take the itty-bitty primitive values, the tiny little free things, and put them in an object-shaped box that costs a little bit of stuff, but we can then store them and manipulate them like objects are. And this is how we interact with the collections class. And one of the big things we use with this is how can we extract data from strings? We use the integer.parseInt or the double.parseDouble methods. I mean, we could use Boolean.parseBoolean, but guess what? Unless you have true, it's automatically false, so we don't even have to worry about that very often. And one of the most amazing things since Java 5 is the power of auto-boxing and auto-unboxing. If I have an array list of integer type, I can automatically take that capital I integer object type and add it into a 7. It's okay because of the power of auto-unboxing. Or I can take a primitive value and auto-box it right in to an integer capital I. So it's a great tool. The wrapper classes make amazing things go even better. So if you do have to actually make an array list of integer, you can just dump the number 7 inside that, or the return value from your calculation method. You don't have to wrap it inside a wrapper class. You can simply just auto-box it straight in, and it's good to go. And that's one of the amazing features we have. One of the things we really need to remember when we're talking about primitives, that primitives, when they're sent as a parameter, we get copies of them. And so if I have a number 7, and I give that 7 to you, the method, then my 7 is totally unaffected. I get to hold on to it and hug it, and it's all good to go, because my 7 will have nothing happen to it unless I reassign into it with the assignment operator, aka the equal sign. When I give you that 7, you get a fresh, brand new, wonderful copy of that primitive value. And that works for every single primitive in the Java language. Whenever I pass off a parameter that's a primitive type, you get a copy of that parameter. Now, this is really amazing. The original, like I said, is unchanged. We have to remember when we're doing that. So, for example, if you have a method that takes multiple parameters and you do some stuff and you reassign inside the method, your original value is unchanged. This is one of those tricksy questions you'll see when you're looking at what happens to a value when you're practicing for the AP exam or other exams like that. You'll have a whole bunch of code that changes the values inside the method. Then you go back to the original call that sent that parameter to it, and nothing happened to the original value. It only happened in the space of the scope of that method. And remember, when we're giving a primitive a copy, or primitive a parameter, it gets a copy. It's its own special version. Your original is unchanged. You need to love it and hold it for your very own. Now, the last thing we want to talk about when we're looking at this is we want to realize that when we're working with primitive numeric types like integers and doubles, and even floats, I know, or especially if we're working with a long, but when we're talking about specifying those values, if I want to write out 4,123,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,0 word them in English terms, like 134,976. Okay? Now, if it's just tiny little numbers like that, it might be okay. But if there's, like, say, 5 zeros in a row or something like that, where I want to make sure I keep track in the right order, I don't want to try and type that out 1, 2, 3, 4, 5 and count them. What I can do is use more of a human-centered organization of that by using a spacer of an underscore. And so I can use an underscore to make it easier to read and write and tell what values are when I'm reading the code. Because if I'm calculating that information, if I need to actually input a value that works for that, for a specific thing, I can specify 1,123,000 like this a lot easier, and I can actually see what we normally put a comma or a decimal in, depending on what locality you're working with for your numeric separators. This is a lot easier to read as a human being than simply 1123000. Same thing with a double. I can do double other equals 0.000 underscore 0000 underscore 0000 underscore 123. And I can get that value specified, and so I can use my human terms of referring to 123 3,000ths, okay, and I can specify that value right there, or quintillionths, or whatever it happens to be of the powers of 10 reference on there. I didn't look at the actual picture when I wrote that, so that's a good problem. But I can refer to that right there. And so that's how I can actually go through and look at that and make it so it's easier for me to write it, especially when I'm writing in code. And I'm doing, say, for example, a math problem inside my actual Java project. And so I can use the underscore to separate values to make it a lot easier to read and write. So again, we can write long or big values by using underscores to separate them. And we can separate them in any simple category. I could have it with 5 numbers in between them if it makes a lot of sense to me. Or I could have 3, 2, 1. Don't do 1. That'd be a really stupid thing. But I can use that to separate stuff like that. So again, that's a way to make it so it's a little bit nicer. Parameters, we get a copy because it makes life a lot prettier. The Java wrapper classes allows us to interact with primitives in an object-oriented way, especially when we're working with strings and parsing data out of it. The best primitive is Boolean because it forms the foundation of computer science logic and true and false values. We have our less common numeric types, byte, short, long, and float, and then char. But we don't have to worry about them very often. And the most common, the most used numeric types as primitives inside Java are the int and double, the whole numbers or integers, and the real numbers, plus or minus 2 billion and plus or minus 2 to the 306th power. Ridiculously huge, but we can do some great stuff. So again, that's a quick little review of Java primitives and how we can do that. Thanks again, and have a great day.